Thank you for joining us today for this laser design webinar focused on the Artec Eva and Artec Spider 3D scanners. We're excited to tell you a little bit about this scanner today. Our goals are to share with you some of the features of the scanners, some of the considerations behind when you use the scanners, and then also show you a couple demos and then talk about good applications for use for both of these scanners. Now the Artec Eva and the Artec Spider, as you can see here, are both small handheld devices that are comprised of a few different key components here that you can see on screen. Really what we're talking about are having projectors, cameras, and LED flash integrated into the front of the unit, and this is really the core technologies behind what we're seeing here. So just to let you know, from a standpoint of a projector-based structured light scanner, we're actually projecting an image onto a part. We're watching that image kind of morph over the 3D shape, and with the cameras we're actually picking up that morphing and obtaining a 3D geometry. Looking at a calibrated known pattern on a flat object, we can tell what that pattern's doing in 3D shape when it morphs over your part. And then the LED flash actually is used for actually illuminating the object that you're scanning. So the projectors on these scanners, we've got the Artec Eva on the left hand side, which has the white light projector at the top. The Artec Spider is actually a blue light projector, and that's at the lower left hand corner or lower right of this screen. The cameras are actually located in a few different places. So the camera that's right around the LED array here is actually a color camera. The other camera is just a grayscale camera. On the Artec Spider, you've got 3 grayscale cameras and 1 RGB camera. And so we're actually collecting both geometry and texture with these scanners, which is an amazing feature of this technology, which is part of why it's so revolutionary. And then the LED flash, as I mentioned, this is something that you can control the intensity with the software and give your object illumination while you're scanning. This could be good for the texture tracking or texture capture when you want to capture the color on the object that you're scanning as well. So when do you use the Eva or the Spider in your application? And a lot of people, when they're looking at this type of thing, they're looking at accuracy, resolution, and then considering the size of the objects that they're scanning too, so looking at the field of view. In this case, the accuracy of the Eva is 0.1 millimeters at its best and 0.03 millimeters or 30 micron for the Spider. So a lot of people look to the Spider for a higher level of accuracy and resolution for maybe more of an inspection capability for different parts. The resolution here, 0.5 millimeter point spacing is the highest you're going to get with the Eva. 0.1 millimeter spacing is the highest you're going to get with the Spider. From a field of view standpoint, it might be kind of tough to see this, but really what we're talking about is about a sheet of paper at the close field of view for the Eva and about a poster board for the far field of view for the Eva. On the Spider side, you're really looking at a postcard up to about a 5x7 picture for that field of view. And to give you a little bit better idea, there's a little example of kind of what that field of view looks like. If you're really looking at the Spider with the blue, you've got a little bit smaller field of view, but again, you're collecting high accuracy and high resolution data. So this is a great fit for smaller parts with higher accuracy needs. The Artec Eva is capturing a lot larger field of view for larger parts. I typically tell people, if you're scanning a human head and below, look at the Spider. If you're scanning a human head and above, look at the Eva. And there are actually applications where you might want to use both for the same project. From that standpoint, let's jump into the Eva demo right now, and we can show you a little bit about what this baby can do. Alright, so for the Eva demo, we're going to actually be scanning a small sculpture. I've got a view of it on the screen right now, also showing our rotary table. Here's my hand. I can rotate this around while we're scanning. So what I'm looking to do initially here today is not going to do a lot of detail, but just show you how the scanning process works. So I'm going to scan this in 3 setups, or 3 positions, merge the information together, and then we'll actually move forward with aligning and creating a watertight STL of this file. So I'm going to press the record button and start capturing data. As I aim the scanner at the object, I rotate slowly around, making sure that my object is always in the field of view. Capture as much information as I can from this position. We're looking at line of sight scanning, of course, so I want to be capturing information from the top, the bottom, the sides. We'll try to get under the chin and up into some of these undercut areas on the back. I'll rotate the object itself. Start the second scan. My subject is face down here. What I'm trying to do is capture enough of the bottom of the sculpture here to be able to easily create a watertight file. I could always scan it just like I did in the first scan and fill some holes in on the bottom, but in this case I want to show the alignment process, so we'll actually do that here very quickly. And one more rotation. What's nice about scanning in multiple orientations as well is that you're able to get areas that may have been tougher to capture from the initial setup, like under the chin, under the nose, things like that. So at this point my scanning process is done. I've got 3 scan files here on the right hand side, scan 1, 2, and 3. What I'm going to do is save this real quick so that we continue to have good data saved during the process. And then we're going to start using the software itself to process and align the data. As you can see, we've got some data of the table, of my fingers, things like that we don't need. So very quickly and easily, we're going to go through here and delete that information. As I move from one step to the other, I actually work through different registration processes. During the initial scan, I'm actually doing a rough registration. After each scan is done, we do a fine registration. And then we'll do a global registration on all the scans together to create the aligned version that we want. So within the editor tool, I quickly use the cutoff plane selector tool to erase the bottom of the information here that is not necessary for our process. So we'll erase that real quick. Get a different view here. Anything that still stayed in the area that we don't want, we can quickly erase. This would be some of the table, or my finger would be in the way here. And now we've got our first scan completed. Our second scan will run through the same process. We'll delete the outlying data points. Adjust our plane up just a little bit. We'll erase that. Again, use our 2D selection tool here to erase anything that remains that we don't want to keep in the scan. Any little stragglers are things that we really don't need to worry about. One other way to do erasing is with a rectangular selection tool, which we can use here. I'm showing a couple different ways to do the erasing process. It's all very easy. The selections are very simple to use, very easy to operate, very user-friendly. The nice thing is we do have some duplicate information here on most of this, so if I erase any of the object itself, it's not a big deal because we have that in the other field of view. Now I'm going to select all 3 scans and align these together. I've got a couple ways to do the alignment, and I'll show you that here real quick. We'll turn this from texture to geometry only for viewing purposes. So you can see we're on the first scan. I might have missed areas under the nose or under the chin. I do have that information, of course, in the second or third scan. So right off the bat, let me just show you one way to align in Artec Studio software, which is the manual alignment process. Just click 3 spots that are fairly close to each other in the scan, or between the 2 scans. Press enter, and then it merges those together. The other way is to actually use the auto align function, which is somewhat humorously named the I'm feeling lucky button. So really I'm just going to press that at this point. The software is going to go through the process to identify what areas on each scan are the same, merge those together based on best fitting features, and now you can see I've filled in some of the areas that I didn't have previously in the first scan, and I'm ready to do my fusion process. So at this point we'll do a quick geometry based global registration. What we're trying to do is get each of these scans to overlay each other and have very uniform distribution of the colors between the two. As you can see here, we've got a lot of the light green, a lot of the blue here, kind of separated. We want to see those interspersed in a more uniform manner, which is what we see here. We see very good quality from each of the scans, and now we can run our sharp fusion. So I want a resolution of a 1mm point spacing. I want a watertight file, and I'm just going to apply that. So as we're working through these scans, of course, right now, before the fusion, we're in just a basic scan, raw scan format. We're not in the triangulated mesh form at any point until we do the fusion. So as it's fusing, it takes all the information from each of the scans and then merges those together into one file that is a triangulated mesh file. So at this point, if we zoom in here and then turn on our wireframe, we can actually see each of the triangulated facets that make up this 3D geometry. Double click this, we've got 730,000 triangles or polygons that represent this shape. I can do a number of things from this point. For the purposes of the demo, I'll actually move to a separate screen, but I could take this, and at this point I can't view the texture because the texture is only in the scan files at this point. I can add those to the Sharp Fusion using this texture button here, and for the purposes of saving some time here, what I actually did was I already did that process, and now I can show you what that looks like after we add the texture to it. So this is a demo part that we've taken to multiple shows. It's been kind of gotten some wear and tear over the years, so this is actually exactly what this looks like. And we have a watertight file here with texture and geometry that we can use for multiple purposes down the road using an STL OBJ type file. So visualization, 3D printing, manufacturing, things like that. So this is the base quick process of doing the scan. Again, we took 3 scans, merged them together, and formed that 3D geometry file. Now that we've finished the demonstration, you can actually see how the scanner works, how easy it is to use, and the type of data that it's collecting. Let's talk about some of the applications for use. There are a number of different things that the Artec Eva is used for in industry, and these uses are expanding all the time based on people's imagination, trial and error, testing of different applications. But here are some that we've really found to be some of the main key areas, and I'll expand on each of these as we move forward. Reverse engineering to CAD. If you have a legacy part that doesn't have CAD, or let's say you've got parts coming off a mold and the CAD information was not provided with the mold when you bought it from a supplier, you may need to generate a CAD model for these, or for your part, for whatever reason. The Artec Eva is a great fit for capturing the information that's going to be the base measurement to create that CAD information down the road. Here you can see we've got some older components of an F100 truck. We've got and some automotive components as well, transmission. I believe this is a carburetor. So you can see we're collecting a lot of good geometry with the Artec Eva on these type of units that then could be created into a CAD model down the road. From a heritage preservation standpoint, it's really tough to capture the essence of some of the objects that are out there that have been made thousands of years ago that you can only see in a museum. A lot of people now are using 3D scanners for collecting information, not only on the 3D geometry, but on the visual aspect. As you can see here, this file is the same on the left as it is on the right. One, we're just showing the texture or color of the object, and the other, we're just showing the geometry. So virtual museums, saving information, knowing that your object, once you unearth it, may decay over time. It's a fantastic way to use for heritage preservation. From the standpoint of body scanning, CGI, and animation, these scanners are top of their class, really. They're able to capture both the geometry and texture, as we've talked about, but imagine scanning yourself, printing out a 6-inch figurine, and putting yourself on the mantle. We actually have customers that are doing that for a living now. That's their business, is creating these mini me's, if you want to call it that. Same file would be used for CGI or animation, just a little bit different format to get that into a Maya Max environment and actually use that for whatever rendering purpose down the road. From a 3D printing and visualization standpoint, because of the color capture and the geometry capture, there's a lot of things that you can do here that you can't do with other scanners. You can see the little mini figurines that we just talked about a second ago. Here you can see a deer mount from one of the engineers here that scanned this at his cabin, and we've got the scan data on the top, the visualized, colored, kind of rendered model on the left, and on the right hand side the 3D printed deer head that's at his desk now. So there's a lot of different ways to use these scanners, and of course, as you start thinking about this more, your imagination just goes into different areas that you could use this. Here are just a few of the options. Now let's get into the Spider demo, and we can show you a little bit about how this is used in a very similar way, but also a little bit differently with the field of view and the accuracy that it entails. Alright, so now we're going to actually move on to the Artec Spider, which is a little bit different, of course, as we've talked about, but uses the same software, same basic process, just meant to scan smaller parts with higher accuracy and higher resolution. So the nice thing is we're using the same windows, same user interface to do all the scanning. We still have geometry and texture, geometry, things like that to use for the registration. Our scan speeds, because of the number of cameras that are on the Spider, of course, our scan speed, instead of being at 15 frames a second as a max like the Eva, it's down to 8 frames a second, of course, and our field of view is much different than the Eva. So as I just press the button for actually starting the scan here, you can see our depth of field information changed from 400 to 1000, now to 170 to 300. So we've actually got a much smaller field of view. You can see I've got a more prismatic and kind of more machined precise part here versus the sculpture that I showed you just a second ago. So we've got a couple things here to think about setting wise, and then we'll get moving. Our texture brightness looks good. I'm going to actually go to our advanced settings and bump up the sensitivity just a tiny bit. This will help us actually collect some more of the information on this shinier part versus having to code it or to have to do an extreme sensitivity. So at this point, I'm in a good field of view. I still have my rotary table, so you can see here's my Lazy Susan cutting board with my targets on it and my part. I'm going to press the trigger button, and away we go. And here I'm actually orienting myself at a fairly vertical angle to try to get as far down into those holes as I can. And of course, as we're rotating, we can actually change the orientation of the scanner itself to capture what we really want. We can come down and get good sidewall data here. I've got this part actually propped up off of the rotary table a little bit to help with the deleting of the data itself, which will be helpful to not have the table so close to the part. And there's my first side scan. We'll flip the part over. flip the part over, and we've got our second side. So just like with the Eva, we're going to capture this from multiple angles and merge the data together. So we'll get a nice outside of the part scan and then focus on filling in the inside. Here I'm focusing again on coming deep down into those holes to get good sidewall information in the hole locations. So I'm really just keeping my scanner focused directly on those as I rotate around the object. And then let's make sure that we get good coverage of the rest of the internals. Now at this point what I'm going to do is actually place the object up on its side. What that's going to do for us is actually give us a good file to merge with that gives us the information of the depth of the part. If you've got fairly flat walls on all sides of the part, it sometimes can be difficult to align it in a way that gives you a very precise alignment from front to back. I'm rotating the scanner a little bit to give a little bit of cross hatching, which will help with the quality of the data in the scan. Merging the angle of the scan frames together. Alright, so the scanning's done for this part. Now it's on to the editing, as we know from the Eva, deleting the outline data, making sure that we've got all the scans aligned, and creating that fusion. So I'll run through this process fairly quickly since we've had a little bit more detail in the Artec Eva section of the webinar. So the autosave makes sure that our raw scans are there in their raw state, and then we're going to actually run through a fine serial registration and then work through the editing. You can see as this saves, I've really only been scanning for just a few minutes. I've got about 2 minutes for the first scan, a minute for the second, and about a minute for the third. We're going to move out of the scan window, and automatically our fine registration will start happening. This does individual fine registrations on each scan independently, and once we run the global after we've aligned it, we can actually take and align all those scans together. But right now this fine registration is only applied to each scan individually. Alright, so into my editor tool, get to my eraser, and I'm going to use my cutoff plane selection tool again. Actually, let's change it up a little bit. Let's use a rectangular selection tool. Because I had this up on blocks, we can actually just delete the table ourselves using this tool here. Then we can use the 2D selection tool to capture a small amount of detail that's left at this point and anything that gets fairly close up here. The other thing now that we've got is the ability, because we've got that side scan, we could delete more of the actual part because we've got redundant data there. In this case, I'll just run through this really quick and show you how this would work using the rectangular selection tool and the 2D selection tool. Erase that. Okay. And the noise that you see up here is actually because our sensitivity filter was opened up a little bit, so we're letting more information in. This will be something that can be cleaned out of the data moving forward without any issue. The last scan that I did was done on the table itself, so we'll use our cutoff plane selector tool. We'll bump that up just a tad to get all the information. We might cut off a little bit there, but that is not a big deal. We're going to erase that. And because I see some rotational noise effects there, I will just quickly remove those from the outside of this. One other way to do this would be to select everything. And let me just show you how that would work. We're going to select all of it, use our 2D selection tool, and deselect just the inside. Alright, so now I've got my 3 scans here. I'm going to move to my alignment tool. We're going to try the I'm Feeling Lucky button on all 3 at one time. Cross our fingers that that works. Alright, so in this case it did not align the scans together with the auto alignment tool. The nice thing is we always can go back to the tool that we know is going to provide the best registration, and that's the manual registration. So what I've done is I've actually changed the final scan that has both sides in it to my main scan, and I can actually do the alignment of each side as manual alignment techniques. So we'll pick a few corresponding points that on each part, of course, that match. Press enter, and then it'll put those together. As we move around to the other side, and we put scan 2 in. Same thing. Enter, and we're good. So now our next step is to do the global registration. In this case we're going to use geometry only, and apply. Now again, we're looking for the uniform distribution between all the surfaces or all the scans that were collected, and this looks pretty good. So I'm going to move on to our fusion settings. I've got good data down into these holes. As I create a watertight fusion, these holes will fill. We'll give it a shot to see how close they get on the... this should fill all the way through as a through hole. I'm kind of wondering how these will do. As I look to do the fusion here, we're going to create a watertight fusion again using our sharp fusion function, which will create the most accurate information for this possible. I'm going to bump this down to about a 0.3 millimeter resolution. I'm going to do watertight like I talked about, and we're going to go apply. Alright, so we've got the fusion here. Again, some of the information, the outlying noise information, has kind of turned itself into a couple blobs out in space. And that's just fine. We can use our small objects filter like we did with the Eva and create a very nice fused model here. I was able to get some really good information in the hole locations here for the through holes. We can see some nice curvature here that was detected. The information on these bosses is good, and we're getting good information all the way around. We actually can read our serial number on the part. If I had done a little bit sharper fusion, we could actually make that out even to a greater extent. But I'm very happy with how this has turned out. Additionally, like we did with the Eva, we could actually duplicate this sharp fusion, create a smaller file for future use down the road. But if I wanted to reverse engineer this part and use it as a base to design something that either was an accessory to this or a new model of this as a base to a design change, this would be a very good file to use. So in all reality, we've got good data from the Eva, good data from the Spider, and I think I'm glad to be able to show you how this information is collected using both of these systems. Alright, so hopefully that gave you a really good idea of the differences between how to use or where you'd use the Spider versus the Eva from an actual demonstration standpoint. You can also see the similarities in how you're capturing the scan data, how you're registering those scans together. You're fusing the models in a very similar fashion. So you can see it's very easy to use both scanners with that same Artec Studio software suite. Now let's talk about the applications for the Spider. A lot of the same ones here that you'd see with the Eva. However, we're looking at probably a higher level of detail and accuracy for industrial parts when it comes to reverse engineering to CAD. And let's actually just jump right into that. So here I've got an impeller and a turbine blade that I've scanned with the Artec Spider. You can see all the detail you need here in the pink image, which is the scan data of the impeller. We use that to create this CAD model on the right hand side, and we're actually creating this with the full history tree importable into SolidWorks. You could actually start designing parts and producing parts with the scan data from the Spider for a high level, very accurately made impeller wheel like this. The turbine blade, same thing. We're actually getting very, very fine detail on the leading edge and the trailing edge of that, and getting very, very good curvature information as well to create CAD information from. From a heritage preservation standpoint, same value with the Spider as with the Eva, as discussed, but now getting a little bit more detail, a little finer resolution, and capturing smaller objects that are being unearthed or discovered. From a body scanning standpoint, we really are looking at, again, I mentioned earlier, the human head and smaller is a great fit for the Spider. In this case, if you want to get very, very accurate information on facial features, maybe you're designing some sort of a custom accessory or an earbud or something like that, this is a scanner that can be used for that type of a purpose. The other thing is, if you've got a small character, some artistic sculpture or carving, to capture that, recreate it, scale it up, and use that downstream for CGI, animation, things like that. Fantastic scanner for that type of purpose as well. From a lab metrology, R&D, and analysis standpoint, we're seeing more people wanting to capture the geometry of different objects for analysis purposes, for measuring, not just to preserve it from a heritage standpoint, but actually to capture geometry and measure and maybe analyze different species over time, things like that. So the Artec Spider is a great lab-based piece of equipment for that type of use. And from a 3D printing standpoint, of course, you can capture anything out there. As long as you can capture it, you can pretty much 3D print it. And so the Spider is a great way to get high level of detail on these parts. I think a reoccurring theme here is just high accuracy, high level of detail, smaller parts for the Spider. Looking at a product visualization standpoint, the Spider is very good for capturing that color texture like we talked about as well, not just the geometry. So I feel like we've kind of mentioned that a lot of times, but some people are actually using this file as their final output for a product visualization standpoint, whether that's for internal use or for consumer use. A lot of different areas to expand here. Comparison-wise then, here's a good example of the comparison between the Eva and the Spider from the face scanning application. Each scan took about the same amount of time, and you can see that on the left-hand side we've gotten the full head, we've got the shoulders, we've gotten under the chin, and we've got the back of the head. On the right-hand side with the Spider, getting the full face, but not a whole lot more than that. So from that standpoint, I think this is a good image to show what you'd kind of expect as far as the base kind of starting point from the size, or the part size that you might want to scan. With the shoe comparison, this is kind of a nice one because you do see both of the scanners have great information from a texture standpoint. You could use either of these the bottom images there for your product visualization. On the top, you can see just how much more detail there is in the scan from the Spider versus the Eva. So that's pretty much what I really wanted to talk to you about as far as the Artec Eva and the Spider today. To give you a little background about laser design, where we come from, and why we kind of care about the Artec systems. We got our start in 1987, and we were an OEM of a line of automated laser scanning probes that are used primarily for metrology grade inspection applications, both on a static CMM and portable CMM arms. We sell those for, like I said, primarily metrology grade applications, but also for reverse engineering. And we also offer a service bureau based out of Minneapolis that does 3D scanning, reverse engineering, inspection, and 3D printing services for customers. So if you need one of the scanners that we are an OEM for, we can sell that to you with the software and solution to kind of cover your needs. But if you really just need a one-off application, we've got a service bureau that will take care of that as well. So one of the reasons I'm talking about the Artec today is because it's not an OEM device for us. We're a reseller of the Artec system along with some others as well. But we wanted to have a number of applications or a number of solutions for our customers that didn't really come from our OEM line. So we are a reseller of some third-party systems that really fill some gaps that the other systems would not cover. So we've done over 25,000 projects successfully in the past, almost 30 years, and we've got a local feel with worldwide presence. So we actually will send our guys on site to do scanning for you at your facility if you need something like that. But really, we have pretty much every base of 3D scanning covered, whether it's something with the Artec doing a body scan, all the way up to scanning a Navy ship. So we can kind of get everything in between there as well. From that standpoint, what I'd like to do as a next step is actually send this presentation to all the viewers, so you can actually have this to reference down the road and view again or share with anybody else in your company that might need it. If you need to contact us for any reason, we would welcome that. You can contact us at info@laserdesign.com or call our main line at 952-884-9648. And now we'll get into the question and answer session of the webinar. Thank you all for joining us. We've appreciated this opportunity to share this amazing technology with you and look forward to opportunities to help you down the road.